So normally I hate giving presentations with equations. I normally try and remove as many equations as I can from my presentation, but I'm not able to get away with it on this one, otherwise I'm not really left with anything to talk about. So hopefully you'll bear with me and I will sort of use the equations to there we go. So hopefully I'll use the equations for sort of illustrative purposes and it will be okay. So this is work based on the work that I've been doing on SENT specimens, building up to the standardisation of SENTs in the end of 2014 in BS 8571. So as many of us will know and appreciate, the single agent occutension test specimen has a lower constraint than an SENB, and it will therefore, for the same material and thickness, give a higher value of fracture toughness. And in industries such as pipeline girth welds under high strain conditions, they are very well established for the generation of JR curves. What the standard is trying to do is to build on the knowledge and practice that has been developed for pipeline girth welds and provide a standard that is applicable to a broader scope of application, so potential for high and low temperature tests, including CTOD and J and single point and R curve. And what we've been doing is a bit of research to sort of support some of the validation to go into that standard. So J integral is a measure of fracture toughness. I know I'm probably just trying to fill in the background in case any polymer people have come in to sit and fill up the back. Characterises the elastic plastic behaviour of the material. It's defined in units of kilojoules per metre squared or newtons per millimetre, and is normally defined in terms of a summation of an elastic component, J, normally based on K, the stress intensity factor, and a plastic component based on the area under the load displacement curve measured during the test. And this work has come out of a need to review the J equations for clamped SENT specimens in BS 8571. The three main equations I'm going to be talking about are the ones that we're already using in BS 8571, and the main one is from a recommended practice published by DNV for pipeline girth welds under high strain conditions, DNV F108, and we sort of, that's the main SENT recommended practice, so it's thought for the standard. We'll take that value of that equation for J and use that as the main one to give people a bit of sort of continuity when picking up and taking on the new standard. And so we've used this one, which was originally based on work by Ahmad et al. From 1991, and we use that for the specimen dimensions, which are also used in DNV, so over square up to square, so W over B ratio less than or equal to 1. But we wanted our standard to also be able to include rectangular dimension specimens, which the DNV specification didn't cover. So we also included for thicker specimens with WB greater than 1, an equation for J from Canmet materials by Shen et al. In 2009. And they originally gave a form for a growing crack. We simplified it to be the equivalent of the DNV one, and you'll notice that the forms are basically very similar. We've got an elastic component based on K and the Young's modulus, and a plastic component based on this eta factor and an area under the load displacement trace and some specimen dimensions. So this one I'm going to call the DNV equation, this one I call Canmet static because it doesn't account for any crack growth, and this is the Canmet, the main equation, which includes increments for crack growth for use with unloaded compliance R curves, and we'll come back to that one. So what's different for the different J equations? We're basically looking at two different parts. We're looking at the different stress intensity factor solutions, K, which are normally based on a sort of polynomial function of A over W. This is going to have a bigger effect where you have lower fracture toughness on the lower shelf. And we're going to look at the different eta factor solutions, which describes the plastic part of the J equation. And again, also normally described as a non-dimensional parameter based on a polynomial function of A over W. I'm only looking at eta C mod, so based on the load C mod displacement curve rather than load-like displacement for simplicity. So for stress intensity factor solutions, this is what we have so far from DNV. This sort of in a basic function here, where you've got these F, and I don't even know what that Greek symbol is. Any Greek people? Anyway, it's defined here with other versions of itself with subscripts 1 and 2, and in themselves quite complex equations. You've also got these Heaviside functions which become 0 or 1 depending on whether you're greater or less than 1. And not forgetting, you've then got these F functions which are given down here, again more Heaviside functions, more summation, so quite a complex set of equations, and there are the coefficients if you should want them. Alternatives are given by Canmet. Canmet have their own alternatives for K, and the Brazilians, Crivella and Ruggieri, similar style where you've got a main term based on the applied load and the dimensions of your specimen, and then a relatively simple polynomial summation based on A over W with a set of coefficients. So these are the ones that would be the alternatives. Now luckily for me, somebody else did this comparison last year, and this paper is really a response to them. Zhu and Magoki from EWI in 2015 went to Arsapi and they said, look, we found an error in the Ahmad equation that's been taken into DNV, it's been taken into BS 8571. You should have a look at this, which is kind of why I went and had a look at it and have re-evaluated the J equations. And this is their figure. They've compared sort of an extra one, I haven't talked about this one, but 3 of the equations that I've shown against A over W, and you can see that the Ahmad, something is going funny after A over W 0.6. It's outside the current validity crack range in the standard, so it's not causing me major concerns about accuracy, but it's not right, and it's enough to make me want to go back and have a look again. But the good news is the other solutions on offer, the Canmet one, the Ruggieri one, are very similar over a wider range of A over W. So we do have some good alternatives to consider. So all I needed to do then is say, well, that was interesting, what about the eta factor solutions? We have a larger number out there. A lot of people have been doing research looking at eta factors solutions for SEMTs. The DNV one includes a sort of arbitrary safety factor of 0.85, nominally to account for weld strength mismatch and strain hardening, but in a kind of nebulous kind of way. Or we'll just add safety factor because we don't know. And again, this is the polynomial functions. Canmet offer one with a larger number of polynomial orders, but considers to be independent of strain hardening. The Brazilians, again, a similar format to the Canmet one, but it gives a different set of these coefficients for strain hardening coefficient of 5, such as high strength steel, for 10, which might be a structural steel, and for 20, which might be a stainless steel. So you have got some ability to account for strain hardening. Another reference, Wang et al. In 2015, provides a sort of two sets of coordinates themselves, which are also functions of strain hardening and the net thickness to specimen width ratio as variables. So you end up with a fairly complex equation, but similar sort of form. Paredes and Ruggieri, again in the Brazilian camp, published a formula including weld strength mismatch. So here, up to now, it's sort of been parent metals. Now we're looking at what about weld metals, and these guys have got a term which includes the weld strength mismatch ratio, the ratio of the weld metal yield strength to the parent metal yield strength. And then the last one I'm going to present, again, you can look these up, but again, another equation for welds, now including, as well as the weld strength mismatch ratio, also the weld width 2H as a parameter, and you end up with really quite a complex equation. I've tried to simplify it here with a couple of summations at the beginning, but it's quite a complex equation, really sort of including all the different parameters you might like to choose. So I thought, well, what do they look like when you plot them together? Which is what I've done. So this is the parent metal eta factors. On both, I'm going to show the weld ones in the next slide. I've plotted the DNV and the Canmet equations over the top of both. So the Canmet is always the black line, and the DNV is always the sort of orange dotted line. And I'm showing the sort of current range permitted in BS 8571. And I was quite pleased because the Canmet seems to be sort of quite a neat fit to the sort of general mean here, but it's sort of playing in my mind where you have particularly high strain hardening, it may be perhaps a little bit over conservative. The DNV, despite having this 0.85 safety factor, still seems a little bit high relative to the other alternatives. And these are the Weld factors. Again, the Morera and the Paredes have got sort of similar trends in terms of as you go to higher weld strength overmatching, but Paredes seems to be a little bit lower. But again, the Canmet seems to be a reasonable, good fit for certainly where there's weld strength even matching. So, as we concluded, well, even with the 0.85, DNV is a bit high. It seems to be higher than what the other references are presenting. Canmet was fairly close to several others. Paredes was perhaps a little bit lower than the other Weld ones. The Wang solutions for the parent materials sort of were quite accurate within the AFW range, but diverged quite strongly. So I'm not quite sure what's going on there. It's quite difficult to say, well, which one's the best, because each of these has been presented against their own numerical modelling and their own validation. So all I'm really doing is sort of saying, well, this is how they compare. I can't really pick one as the most accurate, because all the time we sort of J is being based on an equation and a prediction. But in terms of my job as the British Standard Subcommittee to update BS 8571, I'm feeling fairly confident that if we move the Canmet formula and use the Canmet equation for all specimen types, we're not going to be diverging beyond what's accurate and appropriate. But recognising that actually where you're going to very high weld strength overmatching or very high strain hardening materials, it might need to be looked at again. And I'm not going to make any firm recommendations about the validity limits, but except to sort of raise that as something to keep an eye on. So what difference would it make to our SENT results? And this is what industry is saying. I've done all my tests at DNV, now you're bringing in Canmet, do I have to go and do all my tests again? I compared a load of SENT data, this is single point data, and it doesn't make a great deal of difference. You're still within 10% of what you had with the DNV equation if you move to Canmet. This is data for a whole range of J's, high ranges of J, even down to very low ranges of J. We also wanted to compare R curves, and I'll do this fairly quickly. Most of this based on numerical modelling was done by my co-author Emily Hutchinson, so if I'm a bit quick then it's because this was not the work I did, but most of the SENTs are used for R curves. So what we wanted to do was compare the three main equations, the DNV Canmet and the Canmet tearing one, based on a numerical model. What we did was feed in experimental R curves for different materials, and with what's called the nodal release model. So based on experimental R curve, load the model to a certain J, then release the nodes ahead of that crack to certain crack tearing, and increment that until you've got the R curve. Now what we're doing is feeding in an R curve based on DNV, and then getting the model to define a sort of load displacement trace, and then get it to calculate the three different R curves from that load displacement trace. So the model will coincide more with the DNV equation, so it's really comparing the difference rather than saying in terms of absolute accuracy. And we did this for a number of models, and this is an example of the output that we got, an example of one of the cases that we compared. And I'm not going to put up all 11 cases, but in all examples there was some divergence for some materials, some specimen types, but we could conclude that actually all of the J equations were within about 10% of the predicted one, up to the maximum tearing that would be permitted in the standard. So again, that seems to be agreeing with the experimental comparison with the single results. So to conclude, we wanted to review the J equations from BS 8571. We need to provide accuracy, and a single approach for all specimens would be just simpler. Currently, we were getting anomalies where if you had a B by B specimen and the specimen tolerance was a little bit one way or a little bit the other way, you could end up flipping between two different equations. So we said that that's not going to be appropriate. So this is what sort of driven this review. We knew that the Ahmad equation had an error in it, pointed out by our friends at EWI. And we felt that actually the Canmet equation could be used for all specimen types for BS 8571. Give you a similar value of J, but with an equation that can apply both to single point and tearing without giving significantly different results, but recognising that there may be a need to review that with very high strain hardening or very high weld strength mismatch. I've managed to catch up a tiny bit.
Okay, yeah. Unfortunately, we are running light on time, so any questions to her after the session, please? We have to go on.
Okay.